Welcome back. I've got another nice, beautiful scenery near the coast. This one doesn't give us a specific spot, but maybe a little further north along British Columbia coast. It looks beautiful. I've hiked around places like that near Vancouver Island, and I still think they're using quite a bit of extra color there because the water is so blue. And I know the ocean off the coast of British Columbia is not quite that blue. The nice shallow spots look beautiful as well, though. So I think they can get away with embellishing the color a little bit, which is always nice. Okay, I don't want to go on for too long with the remaining slides. We could talk about operating systems and go into all kinds of directions with all its details, and we could talk for quite a while. So I'll try to finish things up pretty quick, and I've got a few more extra demo stuff to show. We left off looking at the cache for blocks. When you want to read data off the disk, you want to avoid having to read them in over and over again. If you're going to make reference to a file and read the same data, there's no point. If you've already got it in RAM, you can just read it from RAM instead. And we did talk a little bit about this linked list that they have set up, how it's very similar to page replacement algorithms. So as soon as you have blocks in RAM and you're considering maybe bringing in new blocks, then we have to choose to evict some of the blocks that are already loaded. So to make reference to what's already there quickly, they've got the hash table on the left-hand side. So as we were running out of time, we didn't quite get a chance to consider the hash table on the left as in much detail as we would like. But let's say we want a certain piece of data from a file. We get that block and we can hash in order to figure out directly inside the list, instead of trying to go from the very front of the list and then go all the way down to the block we want. Instead, we could use the hash table, get directly into that block right away. So it's much faster to access. The other pieces to mention would be any kind of blocks that we're going to need again. So let's say I referenced one of these blocks for the closer to the front. If I reference them, then I know that means that they are not the least recently used anymore. And so they would move to the end of the list again for the blocks that have been referenced recently. These are the blocks at the end that we want to keep around. So if we're going to evict something, we're going to take the one at the front because it was the one that had been referenced the least recently. This is a really good way to try to set things up. It's just that when we're looking at the figure, you've got to keep in mind that they're not separating the different kinds of blocks that you could have into categories that you might treat differently. So say, for example, we've got inodes, and the information for inodes is quite a bit more important because that's what allows us to figure out exactly where the data for what we want from a file. We go to the inode first. So for that reason, we may reference the blocks from the file again quite a bit. And so they would typically go near the end of the list, or tend to be more near the end of the list. But the inodes themselves, they might not be referenced directly again for a little while, but they're still important. And for that reason, we would not want to evict them. So we could make decisions to keep them in this cache because they're inodes. So we could treat certain data and certain blocks of data differently depending on their category. When we've got this information in the file system, it means that we are currently working on files and they're open. We may be writing data to those files, and to avoid having to do the slow work of actually doing the input output to the disk, we could just update the data on the blocks that we have in this data structure. But that means if our system crashes, then our file system becomes inconsistent. So depending on the operating system you're using, it could be managing some way to recover from the system crashing to save the files so that you don't lose your work on your files. So for example, on Unix, there's a system call called sync, and I'll write that on the slide. So there you have it. So on Unix, we've got system call sync. Now this one will start up and run in the background every approximately 30 seconds. So that way, if your system crashes, you're really only losing about 30 seconds worth of work. So not too bad. In combination with the system call sync, there's a daemon that runs in the background called update. And I know that's kind of strange that that word is spelt probably the way you did not imagine with the way that we pronounce it as daemon. And that program update is the program that's always running in the background that's making those calls to sync about every 30 seconds. Now, Windows is quite different. They've got what's called write-through caches, which means that modified blocks are written back to the disk immediately. And this is actually done one character at a time. So for every character, you're going to do an input-output write to the disk. Now, the advantage of that is that if your system crashes, you're not going to be losing your work. So it may seem a little overkill, but it's a good idea. Okay, some things to consider here. We've got where we're looking at trying to make sure that all of this is running smoothly and that we don't lose the data from the files. We're going to think about the categories of what kind of blocks we've got. So we might want to choose to keep blocks that are essential hanging around like inodes. There may be parts of the operating system itself. Say, for example, if you've got tables and you don't need to keep all of those tables in RAM, then parts of it are stored on a swap disk. So a partition on the disk. So there could be blocks associated with that that are also extremely important. And you'd likely treat those differently from the other blocks as well with these algorithms and data structures for bringing in and managing the cache. So there is something we could do to try to make disk reads more efficient. We could try to read ahead to try to guess the blocks we might need before we need them. So if you're asked to load some block, say it's got some address number like K, well, when it's done reading that in, then our system could try to bring in block K+1 if it's not there already. So we try to schedule these reads to make sure that the cache is filled with what we might need in the future, soon in the future. So we're trying to predict what the next block's going to be. But really, you can only get away with that if you've got a magnetic disk and the disk is rotating. So if you know what the geometry is for the disk, then you can be much better at predicting what you're likely going to need next, because we could talk about how you would store the files on your disk as well. So on this slide, we've got two different ways of arranging your inodes. together with your blocks for those files. You could do it on the right. What we see is each of these cylinder groups. You could have at the beginning of the cylinders the inodes that are associated with all the files, and you would try to allocate the space on that particular cylinder to go along with those inodes. So that way, when you're reading from the file, you know you're going to get the data that's close by on the geometry, and it should speed up reads. Same idea on the left, but they're placing all of the inodes on the very start, right at the outermost cylinder, and then the rest of the files further in. So there could be different ways that you're deciding to allocate files on your disk. Okay, keep in mind that with this, the algorithms you could choose to use and the cache that we're managing for bringing in blocks, even if you're trying to look ahead a little bit and trying to guess at what you're trying to bring in, it's okay if it gets it wrong once in a while, because we don't miss hits with the cache as often as we want to access data on RAM when we're thinking about using the caches that are closer to the CPU. So that's going on at a much faster rate. So when we're thinking about cache for managing blocks, it's happening at a much slower rate. And if it's going to miss once in a while, that's okay. Okay, one point to say about Windows is that if you have an older file system, it might not be managing the space for the files on the disk very well. And so you could look into removing the fragmentation by doing a defrag. And then it places all the files at the beginning of the disk so that you've got all the holes consolidated, and then you now have room to allocate more files. Linux file systems like ext2 and ext3, they don't suffer as much from fragmentation, so you don't have to worry about it as much. And here we're looking at an older file system. It's Unix version 7. So this is a file system where all of the previous topics that we've talked about in this chapter, you see where some of these inspirations come from. And we don't go into too much detail on it. We just want to take a look and see back in history what worked for them. And then if you come across a new problem and you're aware of some of the ways that things have been solved in the past, this could help you to solve problems in the future because you've already kind of got a catalog for what works. So you've got something to compare against. You've got ways of looking at the problem, at least as far as a very limited amount of resources. I think it's good for us to go back in history and think about how did they solve these problems, so that if you needed to, and you're trying to build something like Internet of Things device, where the operating system's embedded on the device, and so a much smaller amount of resources on that computer, then something like this might be useful. So we've got file names that could be up to 14 ASCII characters. They've got that number up at the top there, and then they've got the inode number on the left. It's not storing the directory separator, the /. And you're not allowed to use the character null inside the name anywhere, or ASCII value 0, because that's going to be used to pad the characters on the end of the name if the name's shorter than 14 characters. The Unix inodes themselves, so remember this is just a number pointing to the location of the file, but the inode would contain some attributes, so things like the file size, 3 times, 3 different kinds of times, like a timestamp for the creation of the file or the last access of the file, and then the last modification. It would keep who the owner of the file is, what group they belong to for permissions reasons. And that goes along with protection bits for read, write, and execute that we've talked about a few times. And then the inode would also keep a count of the number of directory entries that point to the inode. I did this as a demonstration for creating hard links. And we saw when I did the ls command and we typed it in the directory, we did ls-la. And of course, I don't have any links there right now, but you can remember the number that I had pointed out, how it increases when you create hard links. So the inode count. This is pretty straightforward figure to understand because the inodes themselves, if the file is very large, we would want more blocks to be able to store the locations of all the other blocks for the file. So if there's so many blocks that it doesn't fit for the addresses to go into the one inode block, then you've got pointers that will go to the beginning of other blocks that are storing more addresses. And it could be tiered into a hierarchy where you've got maybe double indirect blocks like this, or even triple indirect blocks. And then finally, at the lowest level, you've got blocks that store the actual addresses for the rest of the file, the locations where all the data is for a really large file. Okay. This one, we want to think about stepping through what the operating system has to do in order to look up a specific file. So I know it all happens without us really having to even think about it, because when we're working on our computer, we're developing, we're creating files, we kind of take this for granted, but the operating system has to step through each little piece in order to make the file system work. So it has to start somewhere, and where that is at the root directory for a path. And when they want to look up the item within this directory USR, they look up inode 6 that corresponds to that entry. And then that tells them on the disk where to look for the meta information for the file. So inode 6 tells us where we're going to find the rest of the directory USR. So remember, this is stored somewhere on the disk, and it's got the information for where all the other data is for this folder. And it's in block 132. When we go to that block, we've got everything else we can look up within that directory to move on to the next part of the path. And we're looking for AST within this directory. And we find inode 26. Once we get to the metadata, we can see the block number 406 for that directory. And when we step into that directory, then we're looking for mbox. And we can see that's got the address 60, or the inode 60. And so it has to step through this way when we want to work with our files. When we give it a path for something and it finally locates it within the file folder system, it goes from the root directory all the way down. Okay, I know that finishes up pretty quick right there. I wanted to do something a bit different, just to have you think on your feet. And I've got Unity Game Engine open. Now, with operating systems, we're getting into a little bit of the hardware and thinking about how the hardware is working, like the CPU, RAM, the disk. And then I like to talk a little bit about the GPU. So for a graphics processing unit, we can take advantage of many parallel calculations. But even then, you might be trying to do so many calculations that it takes a while. You can see that that took a slight second. I don't know if it caught it on Zoom, but all the triangles started off being almost like a neon blue or a cyan color. And then for these geometries, I assign them a red material. So that way they would be really bright against the blue sky in the background for the game world. And you can see how many triangles I've got here. I created about, I think, 10,000. Let's see. Yep, about 10,000 triangles. For my microphone, I don't know if it'll pick it up or not, but my GPU is starting to do quite a bit of work. Let's take a look at Task Manager, because we can go into performance. And then I've got a listing for 2 GPUs. One is the integrated together with the CPU. The second one is discrete, and it's our NVIDIA GeForce RTX 2060. And it breaks down some of the resources I've got for graphics card. So it's got to send a little bit of data to go along with trying to draw those triangles. You can see it's using up about 500 megabytes. And then the actual GPU itself, how much of the processing is it taking up? To draw the triangles, it's roughly about 40%, I would say, on average. It's going up and down. You can see on the graph how it's just doing many draw calls and then relaxing between frames. And so because all of that takes quite a bit of computational power to do, I may want to not have to calculate that every frame. I know my fan's really kicking in, but what I've got happening inside this program that I've created is when I press the space bar, you're not going to see anything happen, but it actually saves the rendering of all those triangles into a Phong image. So I'll press stop on that, and I'll go to the file. And let's see, since we're talking about file systems this week, I thought this would be interesting to note that one of the usefulnesses of file systems is taking the results of heavy computations and then storing them so that you could use them again later, but with much less computation. So a bunch of triangles all over the place. It's all random. I'm working on something else to use with this. And that's kind of a test to see how many triangles can I draw like that? And what kind of frame rates do I get with it? I think I had roughly around 90 to 100 frames per second for this. But once it's stored as an image, if I wanted to use that again in Unity, I could just load the image and then display that. And then I don't have to have the GPU really calculate anything other than the lookup for the color from this picture, which would take much less computation for it. One of the other spots where stuff like this comes up was in scientific computing. So during my PhD, I did combinatorial searches on the 64 CPUs that my supervisor had funding from NSERC. And I got to use those computers to be able to just load on, do computational search for about a week, let it run, and then we stored the results of what we searched for in files, just in plain text. And we had agreed on what would be a good representation for the graphs we were searching for, and they were just stored in text files. But ultimately, some of the searches were quite huge. We had some files that were, I mean, I got up to like a gigabyte sometimes. I mean, you think if you're going to use a computer system that's much more powerful like that, you've got to get really good at managing many processes. So I would remotely log in to that set of computers, and all I had was the terminal to work with. And I could only execute my processes through the terminal. And then I had to be able to observe how those processes were working. So I typed in commands like top, and I could see which processes were executing, how much CPU power they were taking up, and how much memory were they using on the system. I had to be careful about that because if I had a memory leak, then eventually my programs would be killed by the system because the operating system would not allow it to take up more memory than it should have. So if I saw the memory slowly creeping up, I knew I had a memory leak and I had to go back to my program and find where those memory leaks were and get rid of them. So quite a lot of what we're considering with operating systems, we really got to get you good at considering all the different aspects of your system, how you might manage that with your programming skills. And then make sure you know what you're doing. When you want to run a job, you're going to, in the end, get the results you want, and you can store it on a disk. Okay, not all of you will go on to scientific computing, but it is good to be aware of these kinds of things because if you get a job and if you're going to work remotely, which is way more likely these days, then you could log into a system in the terminal and you'd likely be interacting with that system only in the terminal. Okay, I'm going to hit Q here to get out of the command for top. And then I'll type in clear to get rid of the output for that. I'll probably do a few more demos for top later in the semester as well, because we're going to be getting into threading and we want to be able to see everything that's executing on the system that we've started up. And sometimes you could be debugging and you go to kill your main program, but there's still parts of it that are running. So especially right now, you're working in groups for assignment 2, and your main program is going to be a parent and fork 3 children, one after the other, to execute those processes. And so you could, if you're having problems and you have a bug, you might have to kill your program, hit Control-C, but you might still have those child processes running, and you can check that with top. And you can see the user. So I've got my username. I can see which processes I'm executing. So you can know that when you've started your program for assignment 2, if those child processes go rogue, then you can, we need to show you the commands to how to make them stop processing when you're not directly connected to them. So I think I'll be doing that during the break. We'll have some short demo video for that. What else did I want to show you this week? I'll probably do a little bit more with threading. So we'll have a couple short videos. So I'm not going to do full lecture, but I'll have a few demos over the next week. I hope everyone enjoys your time off. I've got the game jam on Tuesday. If you're looking to do something interesting with Unity, I'm definitely going to be there to talk about that. We've got Will Maher from the Media Arts Department, and he's more familiar with the Unreal Engine. So I know a lot of people like that one, and he could probably talk to you a little bit about that as well. I don't know if he's going to be there for the whole day, but he's definitely going to be there a couple times. And I'm sure you'll meet other students that have some other interesting skills as well. And if you combine your work together, I'm sure you can make some awesome stuff. So I hope you get a chance, even if you can drop in, say hi, you're welcome. All right, with that, we'll probably see you in a couple weeks.